Hello again everyone, welcome back to ptet.chemistry channel. In this video, I will continue talking on Le Chatelier principle. So this is a second part of the chemical equilibrium video, which will be relevant to O-level and A-level students regardless, because it's to do with the qualitative, or what we say is the reasoning behind how the equilibrium will shape or will change as we change the reaction condition. So to recap, so Le Chatelier principle says, if you have a system in equilibrium such that your reactants on the left going to the right, which is the products, but it only applies a system in equilibrium, so that means a reversible reaction. Once it achieves equilibrium, then we say the rate of forward reaction equal to the rate of backward reaction, and their concentrations are no longer changing, they become constant. These were all outlined in the first video on chemical equilibrium, which I will assume you have watched prior to this video, because it's like a prerequisite, so it's called part 1 for a reason. Okay, anyway, so in this video we'll specifically talk about two things: changes in pressure as well as changes in concentrations, and how would these two changes affect a system in equilibrium. All right, so what do we know? We know that in the previous video, we know temperature can affect an equilibrium dependent on whether the forward reaction is exothermic or endothermic. So you can watch those videos on how did I explain them properly. Yeah, so it's better to think about pressure first. Okay, so pressure is defined as the force acted upon a certain area. Okay, when we talk about pressure, we relate it to gases mostly, because gases exert pressure the most. Why? When you think about your solid, well, I'm drawing very simplistic representation of a solid packing, and you think about the gas packing where they are so far apart. All right, you must have done this in states of matter, solid, liquid, and gases, where the particles are just vibrating about their fixed position. They don't move much at all. In fact, your solid is a solid because they stay put, right? They just stay solid. Whereas in the gaseous state, they move all over the place. They keep on wanting to expand, so they keep on hitting the walls of the container. That's why when they hit the wall of the container, if they are inside a container, then they cannot escape, but they exert pressure on the walls of the container. Gases exert a lot of pressure. When we talk about pressure, we relate that to gas most of the time. Okay, the reacting particles, the gases, will exert a lot of pressure, especially inside a reactor. Yeah, inside a reactor, like, cooks up your pressure, cooks up your temperature and stuff. Okay, in terms of concentration, we can think of two types of concentration. We can think the molar concentration, where it's mole per dm cube. Mole per dm cube, I know in O-level or GCSE you do mole per dm cube. It's the same thing, because what we've done is we've done the maths, and then we bring the dm cube to the upper side, it becomes dm minus 3. That is equal to mole over dm cube. How much of the substance divided by the volume of the solution. Okay, or it could even be the volume of the gas, right? Mole per dm cube. How much mole is there per dm cube of the volume? Gas has volume, solution also have volume. Okay, so don't forget that gas also have volume. All right, when we talk about mole is equal to mass over mr, I hope you can see the unit does cancel out, mass over mr. Mr, or relative atomic mass or relative molecular mass, they have their own specific definitions, but their unit tell one story. Their unit say 1 mole of that substance will have a mass of that. Okay, whether it's isotope, whether it's atom, whether it's molecule, 1 mole of this substance will have the mass or something like that. This divided by this will give you the quantity of mole. If I divide by dm cube both sides, I will get mole per dm cube is mass per dm cube over that. So that's how you get the mass concentration as well, with relation to mr from mole per dm cube. Anyway, I think I've gone too far there. We should go back to Le Chatelier principle: pressure and concentration. Pressure affect gases mostly. Concentration can affect, you can think about it, it can affect solution, it can affect gases as well. Yeah, okay, just depending on the units there. So I'm going to give you an example now. So we have done Haber process as your case study previously when we talk about temperature. We are going to use Haber process here again. So reversible reactions to give you NH3. The equation has to be balanced. That's the most important thing. Any equation you write to be balanced, whether you're at O level or A level, it's just the toolkit of a chemist, yeah? When we talk about pressure, okay, when we talk about pressure, we have to count the number of moles of gases. We balance this equation by saying we will need 1 mole of N2. Oh wait, did I say 1 mole of N2? Yes, I did. Because when you don't write anything in front, you are implying that it's 1 mole of N2. Okay? So it's 1 mole of gas. It's very important when you talk about pressure, look for the stat symbols that say it's a gas. Here you have 3 mole of gas. Here you have 2 mole of gas. Look at the stat symbol. Okay? So altogether, the reactant side, which is on the left side, okay, there are 4 moles of gas. Okay, there are only 2 moles of gas on the right hand side, so I don't need to write it. Okay, so how do you explain what happened when you increase pressure or decrease pressure? The explanation comes down to, when you talk about pressure, look for gaseous reactant and gaseous product. Which one is on the left and which one on the right? Total them up. So there are 4 moles of gas on the left, and then you have to state there are 2 moles of gas on the right. Okay, so whichever side has more molecules of gas means that if you have more gaseous molecules, they will exert more pressure because there are more of them. They will hit the wall of the container. They will have higher pressure. Whereas the side with lesser moles of gas, they will have lower pressure as a result of lesser gaseous molecules that can hit the walls, they can exert force on the gas on the area of the walls, and therefore it will exert lesser pressure than the side with higher moles of gases. All right. So what happens when you increase pressure is that this is your change to the system. When you increase pressure, will make the system, or you can say it will make the equilibrium. The equilibrium will oppose the change based on Le Chatelier principle. The equilibrium will want to oppose the change. How does it oppose the change? It opposes the change by decreasing pressure, because you increase pressure, so the system will do the opposite. It will oppose the change by decreasing pressure. The system has pressure as a result of the moles of gases on the left and on the right. How would the system decrease pressure? It can shift to the left or shift to the right, but I want to decrease pressure, so I'll shift to the side with lesser gaseous molecules, because lesser gaseous molecules mean less of these that exert force on the walls. That means lesser pressure. Okay, so in order to decrease pressure, therefore the system or the equilibrium will shift to the side with lesser gaseous molecules. And we already stated in the previous point very clearly how many moles of gas on the left, how many moles of gas on the right. Okay, the gas is important. It's not enough just to total up the moles. Yeah? It has to be gas as well. Yeah. So after all, then we know, therefore the equilibrium will shift to the, well, based on your explanation earlier, if there are lesser gaseous molecule on the right, therefore the equilibrium will shift to the right when pressure increase, because that was our change. Okay, that is to do with equilibrium position. When pressure increase, your equilibrium position shift to the right, it will favor the forward reaction. Okay, it will favor forward reaction, meaning from the reactant to the product. And there's one other thing they'd like to ask as well. What happened to the equilibrium yield? Okay, so it's the amount now. If you favor to the right, your equilibrium yield of this will increase. However, equilibrium yield could mean the yield of anything in this equilibrium unless they specify is of NH3. What if they ask you equilibrium yield of N2? Well, as the reaction shift to the right to favor the forward reaction, then your equilibrium yield of N2 will decrease, because as you shift to the right, more reactants will react to form the products. So the composition of the product will increase, the concentration of the product will increase, the concentration of the reactants will decrease, both this and this. Meaning your composition mixture will have lesser of this and more of that. Okay? So I'm not going to write it down, but it really depends on how far the questions will actually ask you to explain, just in terms of equilibrium position, just in terms of equilibrium yield of single product, or equilibrium yield of the reactants, or just in general, the equilibrium yield of the composition mixture, which I said in the previous video on temperature. When they talk about equilibrium mixture, you have to specify for each of them. All right? Okay, let's talk about separate reaction. So let's talk about this reaction. In A-level chemistry, you will have seen this example where you could take hydrogen iodide and then you heat it and then it will give you H2 and I2. In reality, this reaction exists as an equilibrium, and they've also liked to ask this in O-level as well because this is a colorless gas. H2 is a colorless gas. Because we are doing thermal heating, we are heating it with heat. The thing is, we will not get iodine solid because in the presence of heat, the iodine solid will vaporize easily, and the color of iodine gas, when it goes from solid to gas, that means it sublimes. Sublimation is transformation from solid to gas. Very weak intermolecular forces between the I2 molecules. Yeah? This is a purple gas. A different way of asking this question is, what would happen to the equilibrium when I increase pressure? What would happen to the equilibrium yield of I2 when I increase pressure? What would I see? What would be the observations? Or what would you see? What would you observe as I increase pressure? All right. Well, we need to think about it. When they talk about pressure, we look at the stat symbols. These are gas, gas, and gas. We follow the same idea here. So there are 2 moles of gas. You have to specify it's a gas because we're talking about pressure on the left. And then there is 1 mole here and 1 mole here of gas. So altogether there are 2 moles of gas on the right as well. 2 moles of gas on the left and 2 moles of gas on the right. People might have realized that there's another way. There's another way of writing this. We call it alternative. Basically, we can say there are equal number of moles of gases. Make sure you specify it's gases. We're talking about pressure, yeah? On both sides of the equation. So meaning to say there are 2 moles of gas on the left, 2 moles of gas on the right. Therefore, I can also say there are equal number of moles of gases on both sides of the equation. I can specify 2 moles. This is the same as that. It's just putting it into another worded sentence, I guess, in English. When you have same number of moles of gases on either side of the equilibrium, when you increase pressure, you know the equilibrium will want to shift to the side with lesser gaseous molecules, right? Because you want to decrease pressure. We talked about it in earlier examples here. However, when you have equal number of moles of gases, both sides, they have no preference for higher pressure or low pressure. So essentially, the equilibrium doesn't know which way to shift. Therefore, it doesn't shift anyway because you have the same number of moles of gases on the left and right. So, increasing pressure, in fact, even when you decrease pressure, okay, or you can say any changes in pressure, whether it's increasing or decreasing, will not affect the equilibrium position because you have equal number of moles of gases on the left and on the right, which you need to count for each and every single example. In this example, it just happened to be 2. In other example, it might not be so straightforward being 2, yeah? Okay, so it will not affect the equilibrium position. Therefore, it will not change. Equilibrium position will not change, meaning it's not affected. Therefore, no change to the equilibrium composition of the mixture. If you do not change the equilibrium composition of any of these, that means when you change pressure, increasing or decreasing, the concentration of these are not going to change at all because the equilibrium positions are not affected. All right, so I hope that makes sense then. Next time, I'm going to talk a little bit more on concentration. Okay, Concentrations are quite straightforward as well. I'll use that Haber process as an example because you would have done this previously. But now I want to talk about concentration specifically. Oops, no, 1 is to 3 there. So what is going on is, in that pressure reactor, you need high pressure as I mentioned just now, right? Okay, and the condition, which I'll outline specifically in another video on Haber process. But we know you have high pressure. You have the NH3 that's being produced, and then what happens in the reaction? What happens in industry? You should know how the industrial setup is like. Yeah, you should have seen the diagram of how it is being set up. This NH3 in this reaction is produced as a gas, but then what you actually do is you condense the NH3. When you condense the NH3, basically you're converting gas to liquid, and then you collect and remove NH3 liquid. Okay, why do you do that? Why would you do that? As the reaction progresses, if I can draw a very, very simple diagram, I guess. So there's like a tap, I guess. There's like a tap. Okay, this is a closed vessel. Your gases come in, but obviously there will be a recycling as well of the gases. So any gas that escapes, the gas can get recycled. So you recycle the unreacted N2 and H2 because it's equilibrium, so it's not 100% reaction. But then you will collect the NH3 as a liquid. So the NH3 gas which is formed inside this reactor will go out as liquid NH3 as you do the condensation. Why do you do that? Okay, it's to do with concentration. Okay, so why do you remove the NH3 as a liquid as the reaction progresses? Okay, well, the reason is that when you remove the NH3, when NH3 is removed, whether as a gas or as a liquid, in this case as a liquid, all right, so what happened is the concentration of NH3 would decrease. And this is when we start talking about the Lee-Chatelier principle again. Instead of talking about pressure, we talk about concentration. As we remove this, when it's formed, the concentration of this will go down. What will the system or the equilibrium do? The equilibrium will try to increase the concentration. Okay? Therefore, the equilibrium or the system will try to oppose the change. It will try to increase the concentration of NH3. I wonder how does the reaction increase the concentration of NH3? Well, the reaction produces NH3. So if I want to increase the concentration of NH3, I produce more NH3. How do I produce more NH3? By reacting more products. That's it. By reacting more products and by reacting more reactants and forming more products, I can get more NH3. I can increase the concentration of NH3. So the equilibrium will shift to the right. And so on and so on. You can talk about the equilibrium will favor the forward reaction, and therefore you will get more NH3 as your product. Therefore your concentration of NH3 will increase. Therefore your concentration of reactant will decrease, and so on and so on. Lee-Chatelier principle again. All right. So that's how you use concentration. But there's one particular example that I really, really like to talk about. Is to do with this dichromate 6. All right. Is it dichromate 6? Let me think about it. No, it's not that. Remember now, it's actually a dichromate. What is it? Chromate, sorry, it's chromate 6. This is called chromate 6 ion. As you have known in O-level, something with an "at" refers to a compound with oxygen. This is a compound of oxygen and chromium. It's a chromium plus 6 oxidation state, because chromium plus 4 times minus 2, because the oxygen is bonded in a compound, is a minus 2 oxidation state, unless it's a peroxide, where it's minus 1, where it is not a peroxide here, or if it's molecular oxygen, where it's 0, but it's not a molecular oxygen here. So the chromium here is going to be minus 2 plus 8, there's chromium plus 6. So that's chromate Vi, yeah? There's the Roman numeral there. Okay, so what happened is that if you add acid to it, it can exist in equilibrium to give you the dichromate. Cr2O7, 2 minus, plus H2O. This is aqueous, this is aqueous, this is aqueous, and this is liquid. This is quite a simple reaction that can be done in a test tube. Although I'm aware that chromium chemistry has been taken out from O-level syllabus recently because of the carcinogenic property of it. But it's still around in A-level syllabus, and it's part of transition metal chemistry. They love to ask this in an equilibrium setting because this is yellow. And then this is what we call a dichromate. Well, it's chromium and oxygen, but there are two chromium. It's called dichromate. It is still Vi because the chromium there is 2 chromium plus 7. I'm not going to do it. You can do it as an exercise, just like that. And you can get chromium plus 6 oxidation state as well. Okay, that is orange in color. This is acid. There are two ways of asking this question. Okay, what would happen to the equilibrium as I add more acid? Well, what would happen? The thing is, if they are colorless, you won't be able to see it. But these are colored, so this can be observation. Do they become more orange or do they become more yellow? If they favor the right hand side, you will get more orangey color. If they favor left hand side, you will get more yellowy color. Okay, I'm going to talk about two scenarios. The first one is the easy one. As acid is added, what would you see? What are your observations? Okay, they ask for observation because you can see the color changes. All right, you know transition metal compounds are colored usually. In A2, in A-level chemistry, you'll be expected to explain that. But in O-level or in AS level, you'll just be expected to know, apply in equilibrium, I guess. So what will happen? We are saying that the concentration of acid should write out in full here. I'm just using abbreviation for concentration here. As the concentration of acid increase, then the equilibrium will try to, what would the equilibrium do? The equilibrium will try to oppose the change. It will try to decrease the H plus, the concentration of H plus. How would the equilibrium do that? The equilibrium from left to right, it uses up the H plus. So if I want to decrease the H plus concentration, I just use it up, okay? I just use up more H plus. Therefore, the equilibrium will shift to the right to consume more H plus or to use up more H plus. If I do that, guess what? My equilibrium will shift to the right. That means I will favor the forward reaction. Therefore, see more orange coloration. I hope that makes sense to you. When you shift to the right, you get more orange. You can talk about less yellow. All right. This second bit is the very confusing thing. A lot of people will not expect this. What happens, or what are the observations when you add sodium hydroxide aqueous? What is sodium hydroxide? Na plus and OH minus, right? Do I have sodium hydroxide in here? None of these are sodium hydroxide. That's why it's a trick question. None of these are sodium hydroxide. Why in the world are they asking me sodium hydroxide? Well, first of all, what do you know about sodium hydroxide? It's a base, it's an alkali. That means it can neutralize an acid. I don't have a OH minus in here, but I have an acid in here. Acid as a proton donor can react with a base. So that means the base can react with this. The base can decrease the concentration of this. And when this concentration changes, Lee-Chatelier principle. Okay, so I hope you can see that. As NaOH is added, aqueous. So this is a solution mixture. The solution mixture contains this equilibrium. I add in OH minus to this solution mixture. Then what will happen? It will neutralize. It will react with, or you can say it will neutralize the H plus. So that means the H plus concentration of H plus will decrease. What would the equilibrium do then? The system will try to increase the concentration of H plus. This is a result of the neutralization reaction. This is opposing the result of that by the system in equilibrium. It will try to increase the concentration of H plus. Remember just now, left to right, the forward reaction consume, or it uses up this. So in order to increase back the concentration of this, I have to go backward. I have to form more of it. I have to go backward. It will favor the left hand side of the reaction. Therefore, the equilibrium will shift to the left. It will shift to the left. It will favor backward, or you can use reverse, just be consistent. When I shift backward, what will be the color? What will be my observation then? I'll see the color being more yellow and less orange. So I will see more yellow coloration. Therefore, more yellow coloration. Why am I providing you with these kind of examples? Because they like to ask this in an MCQ setting, A, B, C, D, right? What would be the correct observations? Okay, and some people are lost. They also like to ask you in a structured questions, and some people are lost as well in terms of explaining concentration. And what's the other thing? I forgot what else I was going to say already, but there's really no need for you to remember any of this. But in A level, you would know the color of this because this is your common oxidizing agent. Okay, here this is not a redox reaction. So, I remember now. Chromate 6, dichromate 6. Chromium plus 6, chromium plus 6. No change in oxidation number. This is not a redox reaction. They will ask you, explain why this is not a redox reaction. So basically you just work out the oxidation number and you show there's no change in oxidation number in this reaction. In fact, this reaction is an acid-base reaction. Okay, so that's it from me in this video. I'll talk more about redox in a separate video, and I hope in this video I've outlined how the equilibrium position changes as we change pressure for reaction involving gases, which are very important, as well as concentrations in the context of questions when they are involving aqueous solutions. Or not just that, even the Haber process, we condense it down in that pressure reactor, as you would know about the setup. And that's to do with removing the NH3 and decreasing the concentration of NH3 to try and push the equilibrium to the right so that it forms more and more NH3. Okay, we also talk about reactions that involve color changes because those are the reactions that enable you to make observation very easily and very clearly, and that's all based on Le Chatelier principle. So thank you for watching. I'll see you in the next video, and if you like my teaching style and the way I explain stuff, spread the words and subscribe to the channel and get more friends to subscribe to it, or if you're a teacher, get more of your students to subscribe, and hopefully my alternative way of explaining things would help them to improve their understanding of chemistry. Okay, see you in the next video.